Previously, we learned how to find the homogeneous transformation matrix by first finding the rotation matrix and the displacement vector for each pair of subsequent frames, and then assembling those two components together into the homogeneous transformation matrix. There's another way to find the homogeneous transformation matrix that's kind of a shortcut method. It's called the Denavit Hartenberg method. The Denavit Hartenberg method is a kind of industry standard that you'll frequently see in robotics research papers and industry documentation. This method is faster than the other way, but it kind of obscures the meaning behind the rotation matrix and the displacement vector, and so it's important to first do the other method and make sure that you understand the meaning of each part of the homogeneous transformation matrix before you start taking the shortcut method to the end. In this video, we'll be learning this shorter Denavit Hartenberg method to find the homogeneous transformation matrix. But keep in mind that the matrix that we end up with at the end will be the same as the matrix that we find if we use the other method. So whichever method you prefer to use, you can use. The Denavit Hartenberg method proceeds like this. Step 1 is to draw the kinematic diagram and assign the frames. We have to make sure that we assign the frames according to the Denavit Hartenberg rules. We already learned how to do this previously. Step 2 is to create a parameter table. To find out how many rows your parameter table should have, count up the number of frames in your kinematic diagram and subtract 1. The number of columns in the table is always the same. We always have 4 columns. Each column is for one of the 4 parameters. 2 of the parameters in the Denavit Hartenberg parameter table represent rotations, and the symbols that are used for these 2 parameters are alpha and theta. The other 2 parameters represent linear distances or displacements. The symbols that we use for these 2 parameters are the letter R and the letter D. Let's take a look at the meaning of each of these parameters. To set up the explanation of the meaning of each of these parameters, I'm going to consider 2 frames. I'm going to call one of these frames frame n, and the other frame I'm going to call frame n-1. So in a kinematic diagram, these 2 frames might refer to frame 2 and frame 1, or frame 1 and frame 0, or frame 3 and frame 2. N and n-1 could refer to any 2 frames that are next to each other. That's why I'm referring to them as n and n-1. Let's start by looking at the parameter theta. Theta is defined as the rotation around z n-1 that is required to get axis x n-1 to match axis xn. Keep in mind that this has to include also any theta rotation that is due to the joint. After I've defined each of these individual parameters, I'm going to give you a bunch of examples, and these definitions will make more sense as we look at examples. So don't worry yet if you don't fully understand the definitions. I'm just going to start by laying out these definitions so that we can refer back to them later on. Okay, secondly, the rotation alpha is defined as the rotation around xn that is required to get axis zn-1 to match axis zn. Now keep in mind that even though the axis we're rotating around is the xn axis, the frame that we're going to rotate is the n-1 frame. In other words, we want to ask ourselves, how do we have to rotate the n minus 1 frame around the axis xn in order to get the axis zn minus 1 to match axis zn. To find the parameter r, we look at the distance between the center of the n minus 1 frame and the center of the n frame. The r parameter is defined as this distance along the xn direction. So I'll extend the xn axis and we'll look at the distance between the centers of these two frames only in the xn direction. This is the parameter r. D is the other linear distance parameter. It's defined as the distance from the center of frame n-1 to the center of frame n, measured only in the zn-1 direction. So I'm going to extend the zn-1 axis, and then the d parameter is defined as this distance right there. Okay, let's look at some examples and see if we can better understand the meaning of each of these parameters. Here I'm showing the kinematic diagram of a 2 degree of freedom manipulator that is oriented according to the articulated manipulator. So it's not a full articulated manipulator, but I've started it out as if we're going to be drawing an articulated manipulator. I've labeled the joint angles and I've labeled the link lengths, and I've also assigned the frames according to our Denavit Hartenberg rules. Let's use the Denavit Hartenberg method to find the homogeneous transformation matrix. We're only going to do the second step right now, find the parameter table, because I haven't yet shown you the third step. Let's find the parameter table. We know that our parameter table needs to have 4 columns because there are 4 parameters and we need 1 column for each parameter. There are 2 rotational parameters called theta and alpha, and there are 2 linear parameters called r and d. We need to have a number of rows equal to the number of frames that we have minus 1. So I have 3 frames here, and that means I need to have 2 rows. I'll call them row 1 and row 2. Now, when I find the parameters for the first row, I'm going to be looking at the relationship between frame 0 and frame 1. In other words, frame 1 is going to be my frame n, and frame 0 is going to be my frame n-1. Theta is defined as the amount of rotation around zn-1 between these 2 frames. Zn-1 in this row is z0. So I have to write here the amount of rotation that we have around z0. We have to include both any rotation that is due to the joint variable as well as any rotation that is required to get these 2 frames to match. When you're finding theta, you want to pay attention mostly to the relationship between the 2 x-axes. In this case, my 2 x-axes are already pointing the same direction. That means that the only rotation around z that we have here is theta 1. Let's do theta for the second row right away also. When we look at the second row, we're looking at the relationship between frames 1 and frame 2. x1 and x2 are already in the same direction, so the only rotation that we have around zn-1, that is z1, is theta 2. So I'll write theta 2 here. Now let's move on to alpha. Alpha is defined as the amount of rotation around xn that is required to get the frame n-1 to match frame n. Let's look at the first row. In the first row, we're comparing frame 0 to frame 1. We're going to ask ourselves, how do I have to rotate frame 0 around the axis x1 in order to get frame 0 to match frame 1? We want to be paying attention mostly here to the relationship between the two z-axes. If I would rotate frame 0 around x1 90 degrees, z0 would come down and point out of the page, which would match axis z1. So the amount that I have to rotate frame 0 around the axis x1 is 90 degrees. Let's do alpha for the second row right away also. In the second row, we're comparing frame 1 to frame 2. I want to ask myself, how do I have to rotate frame 1 around the axis x2 in order to get frame 1 to match frame 2? And I can most easily tell this by looking at the relationship between the two z-axes. Since the two z-axes are already pointing in the same direction, that tells me that I don't have to rotate frame 1 around x2 at all in order to get frame 1 to match frame 2. So alpha here is 0. Next, let's do the parameter r. R is defined as the displacement along xn between the centers of the two frames. In the first row, we'll compare frame 0 to frame 1. We want to ask ourselves, what is the displacement between the center of frame 0 and the center of frame 1 in the xn, in this case x1, direction? Here, the centers of frame 0 and frame 1 do not have any displacement in the x1 direction, and so r in this row of the parameter table is 0. Next, let's look at the second row. In the second row, we're looking at the difference between the center of frame 1 and the center of frame 2. How far apart are these two centers? R is defined as the distance between these centers in the xn direction, which here is x2. How far apart are these two centers in the x2 direction? Here, the distance is a2. Previously, when we found the displacement vector and the rotation matrix separately, we had to be very careful to think about whether our answer would be correct, no matter what the value of theta 2 would be. In the Denavit Hartenberg method, this effect is taken care of for us after we plug in these numbers into the matrix in the next step. So here, all we have to do is think about how it is right now in the diagram. Along the x2 direction, the distance between the centers of these frames is just a2. Let's move on to the d parameter. D is defined as the distance between the centers of the two frames in the zn-1 direction. Let's do the first row. Here, we want to think, what is the distance between the center of frame 0 and the center of frame 1? In the zn-1, in this case, the z0 direction. Here, that distance is a1, so I'll fill in a1 in the parameter table. Let's do d for the second row. Here, I want to think, what is the distance between the center of frame 1 and the center of frame 2 in the zn-1 direction, which here is z1. In the Z1 direction, these two centers of the frames are lined up exactly. So D2, that is D in the second row, is 0. I've now finished filling out my parameter table. Before I show you the second step in the Denavit Hartenberg method, I want to show you a couple more examples of finding this parameter table. Becoming good at finding the values in the parameter table simply takes some practice. So let's do a little bit of practice now. I'm going to show you another kinematic diagram. If you think you've caught on to how we fill in the values of the parameter table, pause the video after I've shown you the kinematic diagram and see if you can find the values of the parameter table on your own. And then resume the video and check your answer against mine to see if you got it right. If you're still feeling pretty unsure about how we find these values, just watch the video and see if you can catch on after the next example. Here I'm showing the kinematic diagram for the SCARA manipulator. We know that our parameter table is going to have 4 columns because we always need to have 1 column for each parameter. We also need to have 1 fewer rows than the number of frames. Since I have 4 frames on this manipulator, I need to have 3 rows. Let's call them row 1, row 2, and row 3. I'm going to label the columns for the 4 parameters: theta, alpha, r, and d. It doesn't matter what order you put these parameters in, you just have to include all 4 of them. Let's start with theta. Theta 1 is found by comparing frame 0 to frame 1. Theta is defined as the amount of rotation that we have around Zn-1. In this case, that is Z0. We have theta 1 as being part of the rotation around Z0. We also have to check to see if we have any additional rotation around Z0 that is needed to get X0 to match X1. Since X0 and X1 are in the same direction, the only rotation we have here for theta 1 is theta 1. Let's look at theta for the second row. Here we're going to compare frame 1 to frame 2. Part of the rotation that we have for theta here is theta 2. That's a rotation around Zn-1. In this case, n-1 is frame 1. Next, we have to look to see if the 2 x-axes are in the same direction, and here they are. x1 and x2 are in the same direction. So the only amount of theta that we have here is theta 2. Let's look at theta for row 3. Here we're going to be comparing frame 2 to frame 3. How much rotation do we have around Z2 between these 2 frames? Well, X2 and X3 are in the same direction, so we don't have any rotation due to that. But also, we have no rotation due to the joint because this is a prismatic joint. So theta for row 3 is 0. Let's look at alpha. Alpha is the rotation around Xn that we need to get frame n-1 to match frame 1, or n-1 to match frame n. In the first row, we're going to compare frame 0 to frame 1. We're going to ask ourselves, how do we have to rotate frame 0 around the axis x1 to get frame 0 to match frame 1? Since these 2 frames are already oriented exactly the same, we have 0 for alpha here. Let's do alpha for the second row now. We're going to compare frame 1 to frame 2. We're going to ask ourselves, how do we have to rotate frame 1 around the axis x2 in order to get frame 1 to match frame 2. Specifically, we're going to pay attention to the difference in the directions between the z-axes. Since z1 is pointing up and z2 is pointing down, we would have to rotate frame 1 180 degrees around the direction x2 in order to get z1 to be matching frame 2. So alpha in row 2 is 180. Let's try and find alpha for row 3. Here, we're going to ask ourselves, how do we have to rotate frame 2 around the axis x3 in order to get frame 2 to match frame 3? And specifically, we'll pay attention to the directions of the z-axes. Since z2 and z3 already match, we don't need to rotate frame 2 around x3 at all in order to get it to match. So alpha for row 3 is 0. Let's look at r. r is the displacement between the two frames in the xn direction. So for row 1, we're going to look at the distance between the center of frame 0 and the center of frame 1, specifically in the x1 direction. The distance between these two frames in the x1 direction is a2. So r in the first row is a2. Let's look at r for the second row. Here, we're going to look at the distance between the center of frame 1 and the center of frame 2 in the x2 direction. The distance between the center of frame 1 and the center of frame 2 in the x2 direction is a3. Okay, let's try to get r for the third row. Here, we're going to look at the distance between the center of frame 2 and the center of frame 3 in the x3 direction. The center of frame 2 and the center of frame 3 is exactly lined up in the x3 direction. So r here in the third row is 0. Lastly, let's fill in the D column. D is defined as the distance between the centers of the two frames in the zn-1 direction. So for the first row, we're going to look at the distance between the center of frame 0 and the center of frame 1 in the z0 direction. Here, that amount is a1. Now, let's look at the second row. Here, we're looking at the distance between the center of frame 1 and the center of frame 2 in the z1 direction. When I try to write this amount into my table, I notice that I forgot to label one of the link lengths. I have a link length here that I didn't label. I'm going to fill it in now and call it A5. So D for row 2 is A5. Lastly, let's do D for the third row. Here, we're going to look for the distance between frame 2 and frame 3 in the zn-1 direction, which here is the z2 direction. The distance here is a little bit tricky because we have both a link length and also a joint variable. The distance here is a4 plus d3. You might be wondering why I made a4 plus d3 positive, even though they're pointing down. Note that in each of these parameters, we're looking in a specific direction. So in this case, D in the third row, we're looking at the Z2 direction. The Z2 direction is positive down, as indicated by our Z2 arrow. That's why I made A4 plus D3 positive in this row of the table. If I had instead defined Z2 to be up, which would be allowable in our Denavit Hartenberg rules, in that case I would have had to make A4 and D3 both negative. Now, as you do this method for more and more complex manipulators, it's a good idea to have some ways to check yourself for errors as you go along. One of the ways to do this is once you have this parameter table filled out, you should have in your table every one of your joint variables and every one of your link lengths appearing somewhere. If I had filled out this table and would see that, for example, theta 2 did not show up in my table, that would be a clue to me that I'd done something wrong in my table. Since the joint motion theta 2 actually does affect the rotation and position of the end effector, it needs to show up in my table somewhere. Similarly, if I would have filled out this table and found that, say, A4 did not show up, I would know that I had done something wrong, since the distance A4 really does affect the position and or rotation of the end effector. It must show up in my table somewhere. I will be showing you some more complete examples in the next video, but before we finish this video, I need to show you the second step of the Denavit Hartenberg method, which is how we use this parameter table to get the homogeneous transformation matrix. It's actually a simple step. The hard step is finding this parameter table. If you've done this part correctly, finding the homogeneous transformation matrix is trivial. Once we've found our parameter table, we can find each homogeneous transformation matrix from frame n-1 to frame n by plugging in the parameters that we found in each row of the table one at a time. And we plug them in like this. In this matrix, I've used the letter C to represent the cosine and the letter S to represent the sine. So suppose you want to find the homogeneous transformation matrix between frame 0 and frame 1 like this. 0 to 1. In this case, n is 1. All we would have to do is plug in the 4 parameters that we found in row 1 of the table. Here, n would be equal to 1. Then, let's suppose that we want to find the homogeneous transformation matrix from frame 1 to frame 2. We can set n equal to 2. Find all of the parameters from the second row of the table and plug them into this matrix and compute. Then, if we want to find the homogeneous transformation matrix from frame 1 to frame 3, or that is from frame 2 to frame 3, we set n equal to 3, plug in all of the parameters from the third row of the parameter table to find this matrix. Then we can find h from 0 to 3, all the way from the base frame to the end effector frame, by multiplying these 3 matrices that we found, h01 times h12 times h23. Keep in mind that the meaning of the homogeneous transformation matrix is the same, whether you found it from the method where you find the rotation and the displacement separately, or if you find it by using this Denavit Hartenberg method. In both cases, this part of the homogeneous transformation matrix tells you the rotation matrix, and this part tells you the displacement vector. So once you've found your homogeneous transformation matrices, you can troubleshoot and check your own work by checking to see if your rotation matrix and your displacement vector make sense, regardless of which approach you use to find the homogeneous transformation matrix. In the next video, I'm going to show you some more examples of finding the parameter table and then the homogeneous transformation matrix using the Denavit Hartenberg method.